Hi everyone. Today we're going to be learning about what's called activation energy and enthalpy, which has to do with how a reaction is able to go to completion. How are the components of that reaction, those reactants, able to actually come into contact with one another and create a reaction in order to happen? And then what kind of things can we do to a chemical reaction to speed things up? How can I make it go a little bit faster? So when we talk about chemical reactions, the basis of our understanding of what you need to know is that in order for a reaction to happen, you must have your reactants come into contact with one another. They have to collide. So that's why we call it a collision theory. It's the theory that it has to collide to come together in order to form a reaction. But there are some times when you might mix two reactants together, but there isn't a product that's formed. So they just sit there. Why are they not reacting? Here are some things that could happen. They could hit in a location where maybe it's not favorable for them to create a chemical bond, meaning no reaction. Okay, so this would result in a no reaction. Maybe the particles don't have enough energy. They're too cold, right? So maybe I made the situation, I wrote like that. Maybe I made the temperature too cold and that caused the reaction to not move fast enough, meaning they don't have enough energy to collide, meaning they don't collide and they don't react. That would result in a no reaction as well. And then sometimes there's this what we call almost like a middleman in a chemical reaction where it's not the reactant, but it's not the product. It's somewhere in the middle of what I need, and it's happening as the reaction goes forward, and eventually it goes away and turns into the product. But when it's in this activated complex phase, this middleman, this intermediary between our reactants and our products, you could have it turn back into a reactant or fall forward and turn into a product. So if that's happening, we might have a no reaction. So just because I mix two chemicals together doesn't mean I'm always going to react them. There have to be certain conditions that are in place. So how do I represent a reaction that's actually happening? The way that I show this is what is called a potential energy diagram. So in a potential energy diagram, you have your reactants over here. They will eventually form the products down here. And as we can see, we have a balanced chemical reaction above. We have two reactants coming together to form the singular product. What it's showing on our y-axis is potential energy. So how much potential energy do those materials have? And then across the bottom of the graph is just time. So this is showing how energy can be stored as reactants and eventually turn themselves into products. What we can also see on this graph is that we have this little thing at the top, which is what we call the activated complex. You'll notice if you look in the balanced chemical equation, A2B2 isn't anywhere to be found, which makes sense because it's an activated complex. It's not necessarily a reactant or a product. It's somewhere in between, and it's not going to last for a long time. So this diagram is showing us the change in energy, how we start off with our reactants at 25 kilojoules, and we end with our products at 5 kilojoules. That means the reaction lost 20 kilojoules. We're down 20 kilojoules. We used them up. And that got released. So that's something that we would potentially see between our reactants and our products. So how do we actually use these? When we're looking at a potential energy diagram, the first thing we want to consider is how much energy it's going to take to get from our reactants down here up to our activated complex. Because in order for me to get to products, you can almost imagine this kind of like a roller coaster ride. Like when we're going in a roller coaster, we have to go up the hill, up the hill, up the hill, up the hill, up the hill. Eventually we get to the top, and then we're going to start to fall down the hill, and that's where our products are going to be. So our activated complex is actually higher potential energy than the products, okay? So we have to go up really high in order to get this reaction to occur. So keep that in mind as well. So when I'm trying to figure out the activation energy, it's the minimum amount of energy to start the reaction and form the intermediate. So if I am adding, I have my reactants together, they're coming in contact with one another, they're making collisions, but my energy is only here, nothing's going to happen. It's just going to sit there and I don't see any products being formed. So this is how much energy it takes to form that activated complex. So another thing that we see on this diagram is something called enthalpy, or delta H. So enthalpy is often called the heat of the reaction. It's the net gain or loss of stored energy. So whether or not it goes up or goes down. So what you do when you're trying to figure out if your delta H is positive or negative, if your reactants are less energy than your products, you have a positive delta H. If your reactants are greater in energy than your products, you have a negative delta H. And if we look here, our energy down here for our reactants compared to our products up here, this is a positive delta H value because our products are higher up than our reactants. So this would show a net gain in potential energy because it's gaining energy. So we can see that because delta H is looking at the comparison between the activated complex, and we're looking at not only delta H and also the activation energy, we can solve these if we know what these values are. So how much energy was required to go from reactants to activated complex. That's what's called our activation energy. The difference between reactants and products is our enthalpy, or our delta H. So I can find all of that so long as I have an equation and I have actual numbers over here on the side that I can read from. As long as I have that data, I can solve these problems pretty easily. So if we look at this particular problem, notice how our reactants are higher in energy than our products. So this is an exothermic reaction, okay, where energy is lost, energy is released out into the atmosphere or wherever else. So because our products are lower in energy than our reaction, this is going to be negative. Energy is lost as a result of this reaction, okay? And we can also see on your previous slide, I think this is what we can also see is when we look at these reactions and we know that endothermic is going to have a positive delta H, exothermic is going to have a negative delta H like we saw in the previous slide. Let's look at this reaction first. So if we look at our reactants, they're at 75 kilojoules, and I look at my products, the potential energy of my products, it's 225 kilojoules. So if I'm trying to figure out how much energy it takes to get from reactants up to the activated complex up here, that's going to be EA, okay, or what's called activation energy. So how much energy does it take to get up to that activated complex? So if our reactants are at 75, our activated complex is at 300, we're going to take the activated complex energy minus the reactants. So in that case, it's going to be 300 minus 75, which is 225 kilojoules. So what that means is I need to put in 225 kilojoules just to get the reaction to start. The delta H is going to be the difference in energy between my products and my reactants. So I'm going to take the energy of the reactants, or sorry, the energy of the products minus the reactants, which in this case is 225 minus 75, which gives us a value of 150 kilojoules. And it's positive because I have to put energy into it, and my products end at a higher energy than my reactants did. So that means this is an endothermic reaction where I'm putting energy into it. So looking at this particular problem, sometimes we can see reactions that are reversible, meaning I could form the reaction going this way, or I could be working with AB and turn it back into A2B2. That is sometimes possible. It just depends on the reaction. So if we're looking at these reactions, we have to see whether or not it's going to be more favorable energetically for the products to turn into reactants versus the reactants to turn into products. So how can you tell which is going to be faster? You're going to compare the activation energy. The lower the activation energy, the more spontaneous. So I'm going to write that off to the side. And more spontaneous just means it's going to happen. So think like if something has to have energy to react, it's going to react faster if it needs less energy. Well, if we look at the forward reaction, which is, bringing our A2B2 up to here. So this would be our delta H of the forward reaction, or not delta H, I'm sorry, your activation energy of the forward reaction versus the activation energy of the reverse reaction. So imagine we were going, this way up the graph. I need to put in so much more energy to reverse this reaction and make it turn back into A2B2. It's going to take a lot more effort. So if I look at this, the forward reaction going in this direction is faster than the reverse reaction, which means the forward reaction is what's going to happen. Okay, so that's how you can tell what it is that's going to happen, whether it's the forward or the reverse. So when we look at this, it's always going to be the lower activation energy that we're going to see actually occurring. So if we're looking at a potential energy diagram, and maybe let's say we're looking at a catalyst. So if we remember what a catalyst doesn't react in a chemical equation. It doesn't participate. But what it does is it lowers the potential energy of an activated complex. So what that means, if I add a catalyst into this reaction, I don't have to bring my reactants up as high of energy. Okay, so I can reduce the amount of activation energy that's needed, and if there's less activation energy, the reaction happens faster. So a catalyst will sort of reduce what's happening in terms of how much energy is needed for that activation complex. It just bumps it down a little bit. So let's say we're looking at this practice problem. This is a very repeatable problem that you will see on the homeworks, you'll see it on the test, you'll see it everywhere. So these are pretty easy to do as long as we can see them. So we're going to do some labeling. We know that our reactants are down here. We know our products are over here. We know the activated complex is up here. So what I'm going to do is start filling in the information that I know. So I know that the potential energy of the reactants is 50 kilojoules. The products is 100 kilojoules. And the activated complex is 250 kilojoules. So to find the activation energy, you take the activated complex potential energy, subtract it by the reactant potential energy. So in this case, it's 250 minus 50, 200 kilojoules. So it takes 200 kilojoules to get up to the activation energy. The delta H then is the difference between products minus the reactants, which in this case is 100 minus 50, which is 50 kilojoules. This is a positive value. So that means this in the forward is going to be endothermic, okay? So it's going to be endothermic. We also see if we go in the reverse reaction, so if we go in the other direction where we flop what would be, so I'm going to kind of color code these and make them red. These would become the reactants and these would become the products, right? So you can kind of see that there. In that case, the energy I need to get up to the activated complex, if I'm going in the reverse reaction, is only going to be 150 kilojoules, okay? Because it doesn't have to go up as high because the products are a higher energy. And the difference between the products, and the reactants in the reverse reaction is going to be negative 50 kilojoules. So it's going to lose 50 kilojoules going from here to here. It goes down in energy. And then if we were drawing in a catalyst to see how that would change things, all it would do is just reduce the amount of energy that this activated complex needs. So the big thing with this lesson is being able to find not only activation energy, So that's going to be what we call EA, but also enthalpy, delta H, of a chemical reaction using that diagram. Then we're going to determine if it's endothermic, meaning it has a positive delta H, or exothermic, negative delta H, by looking at these diagrams. So compare those numbers of kilojoules. And then how will a catalyst affect that potential energy diagram? So if you need to, go back and review some of this stuff, but hopefully this isn't too complex. And if you have any questions, please let me know.